Okay, so now we can define the trig function. So as I said in the previous video, for each number t, right, each real number t, you can associate it with a unique point p on the unit circle. Again, let me just quickly say, you basically, if t is 0, you take p to be the point 1, 0. If t is positive, you're going to walk counterclockwise along the unit circle until the path you form is t units long. P is the point you end up at. And if t happens to be greater than 2 pi, you're going to travel the entire unit circle at least once. If t is negative, the only difference is that you go clockwise. So if t is positive, you go counterclockwise. If t is negative, you go clockwise. But now we're ready to define these trig functions. So the idea here is, what we basically do is we're going to use this point p to define the trig functions at that number t. So as we can see here, cosine of t is x, the x coordinate of that point. Sine is the y coordinate. Now if x is not 0, of course, the tangent function we define this way, and so on and so forth. And the only one missing here is cotangent, but I think that's on the next, right there. You do have to be careful because, as you can see from these formulas, that if x is 0 or if y is 0, basically if your point P happens to be on the x-axis or the y-axis, then not every trig function will be defined. And that's really what I'm saying here. In particular, if you're on the y-axis, your x is 0, so your tangent function, because you're dividing by x, and your secant will not be defined. And again, that's just because you'd be divided by 0, which you never do. And likewise, if you're on the x-axis, your cosecant and cotangent are not defined. So just to make it a little bit clearer, let me just draw again the unit circle. Okay. T again, this is the unit circle. Here's y, here's x. Again, the radius is 1. So you give me any real number t, walk along the path, right? The point you end up at, so this is t units long. Again, here I'm taking t to be positive. This point, let me see if I can, let me draw it light blue. A little colorful. The point P is the point you end up at. That's going to have coordinates x, y for some x and y. And then you have cosine of t equal to your x, sine of t is equal to your y, and so on and so forth. Let's do an example. So let's suppose the point t is such that the point P we end up at is here. Okay, well, we can get the trig functions easily. Again, it's just using the definition. Notice that your x-coordinate here is -1/2. Your y-coordinate is negative radical 3 over 2. And then we're just using the trig function. So cosine of that t, I don't know what that t is, but for the moment, that doesn't matter for the moment. Cosine of t we have is -1/2, right? That's your x. Sine of t, which is your y, right? Sine of t is y. That's negative radical 3 over 2. And you get the other trig functions. There is some basic algebra that I'm actually doing here. And that's really what this is saying also. So here I'm actually rationalizing because I don't want 1 over radical 3. What people generally do is they write it as radical 3 over 3. And that's just the algebra illustrating it. That's all. Okay. Now we are ready to define the trig functions for any angle theta. Okay, so let's suppose theta now is some angle in radians, but let's assume it's drawn in standard position. And again, what does that mean? Well, that means the vertex of the angle is at the center, at the origin, okay? And the initial side is going to coincide with the positive x-axis. In other words, the angle is going to look something like this. Although here, I'm assuming theta is such that the terminal side is in the first quadrant. That doesn't have to be the case, but let's stick with this for now. So this is our theta now, okay? Again, this is what standard position is with the terminal side in the first quadrant. Basically, the initial side, again, has to lie on top of the positive side of the x-axis, and the vertex is at the origin. Okay, now let me draw the unit circle. Okay, so now notice the terminal side is going to intersect the unit circle. Again, this is the unit circle at some point here. Okay, that's going to be our P. Good. Now, also, not only that, P is going to be associated with some number T, right? Basically, if we were to look at the arc length here, okay, this arc length here, right? That arc length is going to equal to T for some number T, for some T that's positive, okay? Then, if you remember the arc length formula, S equals R times theta, right? Although R in this case is 1, right? Because we have the unit circle. So in this case, we actually, and S in this case, as you can see, is just T. So we have T is equal to 1 times theta. So in other words, we get T is equal to theta. So as a real number, T is actually equal to theta. And this is also saying, if you think about the units, theta is equal to T radians. Now this is just the idea, because again, I'm assuming theta looks like this. But it turns out in general, if you use this idea, this is always going to happen, regardless what angle theta is. Okay? You're always going to get theta equals T radians. They show the general case. They actually show, all the cases in the book. So I'll let you read that on your own. But because theta is going to equal to T radians, this is actually why we make this definition. So if you have an arbitrary angle theta in radians, right, it's going to be T radians for some T. This is how we define, down here, the trig functions. So sine of that theta is equal to sine of that T, cosine of theta is cosine of T, and so on. This is actually the definition here, okay? So this here is the definition. Good, okay? Keep in mind also that, well, notice that if theta is an angle, notice here we actually have the trig functions defined at angles and at real numbers, okay? Generally from the context, that's what I'm saying here, that the context will make it clear which one we're dealing with. Although, as you can see, the definitions are almost identical. So really, I guess from an algebraic point of view, it's not going to be too much of a difference. Okay? But again, this is the definition. They have more cases in the book, in the textbook that is. I was just trying to illustrate up here where this definition comes from and how it's related to the previous one. And again, it really just has to do with the arc length formula and being in standard position and so on.